All right, 9.9, representation of functions by power series. So we're going to be taking these, like it says, functions, and they're not going to be done in the way that we did before by going through Taylor polynomials and creating the Taylor series. We're going to actually use what we know from the geometric series for a couple reasons. Number one, if you look carefully at what this function is represented as now, it looks like the sum formula of a geometric series. In other words, geometric series, I guess I don't need a sub 1 there. Geometric series is equal to, or its sum, so the summation of this is equal to a over 1 minus r. So we're taking the sum and we're creating the series from it. It's all going to be revolving around geometrics. So it says, as you carefully read the title of today's section, what words pop out as being a significant change from our previous sections? You should notice the word function. The title has strayed from specifically dealing with polynomials to expanding our discussion to include a variety of functions. We've already discussed e to the x and some trig functions, but those provide fairly easy patterns to create a series out of. Some of these other functions may not create those same kind of formulas as easily, so we're going to use this model instead. What methods exist for creating a power series? Well, again, depending on how long you stare at this, you might not recognize right away that that looks like the sum formula, but we are going to be using geometric series to do this section. So that being said, it says let's look at the fourth degree Maclaurin polynomial. You remember that a fourth degree Maclaurin polynomial requires 4 derivatives, and each of those is going to be evaluated at 0. The derivative of this function would be negative 1 minus x to the negative 2, and because of the chain rule, we have to multiply by a negative 1. That negative and that negative cancel, leaving just 1 minus x to the negative 2. Then I get negative 2, 1 minus x to the negative 3 times negative 1, which becomes 2, 1 minus x to the negative 3. Negative 6, 1 minus x to the negative 4, which becomes which becomes times the negative 1, which becomes 6 times 1 minus x to the negative 4. And then finally, negative 24, 1 minus x to the negative 5 times negative 1 becomes 24. So what we're in essence doing is creating positive numbers when all is said and done. When you evaluate each of these for 0 and plug 0 into the formula, 0 plugged into the first one is going to give you 1 to the negative 1, which is 1. Then we're going to get 1 to the negative 2, which is 1. Then we're going to get 2 times 1 to the negative 3, which is 2. 6 times 1 to the negative 4 is going to be 6. And 24 times 1 to the negative 5 is going to be 24. It follows that we have this Taylor polynomial, right? This would be the formula that we use generally speaking, and if we actually plug in the values that we get, f of 0 is 1, the x minus 1 to the 0 stays 1 over 1, so we just get 1 for our first term. F of 0 becomes 1 times x squared over 1, so x. This is incorrect, so that should be a first derivative, this should be a second derivative, this should be a third derivative, and that should be a fourth derivative. The second derivative is 2 times x squared over 2, which would just be x squared. The third derivative is 6, which matches the 3 factorial, so we just get x cubed. And the fourth derivative is 4 factorial, so those cancel, leaving just x to the 4th. Question is, can we make a series out of this? And absolutely, this is an easy one. This would be the series from, now again, if I'm trying to come up with this term, I can't start with 1 and plug in 1. We know it's x to the n, right? to get that to match the 0 that I need for an exponent here, I'd have to start at 0. So there is an alternative. Sorry, to the infinity. I don't know what I'm thinking here. There is an alternative. You could have gone from 1 to infinity and did n minus 1 for your exponent, but I'd rather not in this case. So if so, what kind of series is this? This is a geometric series. And 1 over 1 minus x is equal to the sum. So a is 1 and r is x in this case. Okay. Says let's use the same function as before, but center it about c equals -5. Is there a shortcut instead of having to go through the entire process, meaning instead of taking the derivative each time and having the -5, or rather the +5 instead of the -0, that actually made it for some easy manipulations. But is there a way to jump from the beginning to the end more quickly? Well, if we know, for example, that this geometric series is of this form in some formula, then we can use that to our advantage by starting with the formula and working our way back to this geometric series. Here's how. So the first thing I'm going to do is center this x value. Now watch very carefully. To center it, I know that I have to have x plus 5 together in parentheses. But what I just did was completely change my original formula. These are currently not equal. They will only be equal if I balance it. Well, what did I just include in my denominator that wasn't there? You might say +5, but technically with the negative in front, it's a -5. So I balance this with a +5. I'm going to rearrange what I have a little bit, and technically I have 1 over 6 minus x plus 5. Now if you remember, the geometric formula always has a 1 in that position. So what would I have to do to get a 1 here? Well, if I divide everything by 6, then I would in fact have 1 in that position. Now I have what I can rewrite as a geometric series, knowing that geometric series start at 0, go to infinity. The numerator is my a value. What's in parentheses is my r value. And there I go. The amount of work that I just did was fairly minimal as compared to taking all of the derivatives and evaluating all of the derivatives and then finding a pattern and so on. I'm able to go from this formula, generate the series that it came from with a few short steps. I see that it's centered around -5, and I see some other pieces of information here. And I'm going to be able to do some manipulations from this formula fairly easily. But before I get to that, get more in depth with that, we're going to practice putting some more of these in geometric form. Starting with 4 over x plus 2. Write it in the appropriate form, in its geometric form, meaning right now it's in x plus 2 in the denominator, but the geometric formula has the 1 written first, has the constant written first, so I'm going to do that here as well. I'm going to create 4 over 2 plus x. We're going to go through this pretty slowly. Now it's supposed to say minus x. But if I put a negative here, what am I really doing from this function to this function, but multiplying by -1? And I'll only maintain equivalency if everything gets multiplied by -1. Okay? Now I'm going to center the function. Centering the function requires me to write, instead of x minus c, I'm going to write x minus 10. And I'm going to remember that I'm not actually subtracting 10 here, but because there's a minus out front, I'm adding 10. So to balance this out, I have to subtract 10. By the way, the order that I'm doing this isn't necessarily the only order to go about doing this. So keep that in mind if you find something that becomes a little bit easier for you. This becomes -4 over -12 minus x minus 10. Divide everything so that we get 1 minus r. Well, if I get 1 minus r, I have to divide everything by -12. Now be careful here. I get 1/3 in my numerator. I get 1 minus, and I want you to keep this with the formula, because the formula has to say 1 minus r, so this whole r has to be maintained. Okay? Keep going. It says substitute a and r into the geometric series. My a is 1/3, and my r is x minus 10 over -12 to the n. It goes on to ask a question that we had in the last section. What's the interval of convergence? Okay, well, if you remember, a geometric series is convergent if the absolute value is between 0 and 1. The absolute value of x minus 10 over -12 between 0 and 1. In other words, if the absolute value is less than 1. That means that the absolute value of x minus 10 over regular 12 has to be less than 1. Right? When I take the absolute value of -12, it becomes 12. Which means I'm going to squeeze, or I won't get there just yet. It means the absolute value of x minus 10 has to be less than 12, right? If I multiply by 12 on both sides. All right, let's continue this thought process over here. Absolute value less than means that I'm going to be stuck between -12 and 12. Let's finish this up by adding 10 on all three sides, and I get -2 less than x less than 22. That's my interval of convergence. Now, why would I not test endpoints here? We did in the last section, and that was because in when I used my ratio test, I had a possibility of having endpoint convergence. I had a possibility of having a convergent series on either side, so I needed to figure them out separately. But if I plug in -2 into my geometric series, if you remember the reason for, again, I wrote it here, but in a geometric series, anything, I don't know why I wrote DISC, DI, oh my gosh, my brain. Any ratio that's greater than or equal to 1 is automatically going to be divergent. So if I plug in these endpoints, these are the two numbers that gave me 1. I used 1 in my manipulations here. So -2 and 22, when I plug them in, will give me 1, and that's part of my divergent endpoints. So I'm only convergent within the interval. Okay? Question goes on to say, how can we be sure that the series we used to represent our function was in fact the appropriate series? And a way to check would be by long division. I'm checking this before I go any further with this discussion because this looks awfully strange to me all of a sudden. Long division. Let's skip this portion. I can always come back to it. Okay. Determine the power series representation for the function below centered at -2. So you're going to see as I go through this process, sometimes I don't do things in the same order every time. But as long as I'm making a mental note about having the minus in the denominator, having the first term be a 1, and making sure that it's centered, how I go about doing that isn't so important as long as my end result is, in fact, in the right form, and what I did to get there was legal. So first thing I'm going to do is, at the same time, write this in the correct order and center it. So again, I already did something in a different order than I've done before. It may or may not work in my favor, and that's okay. I end up with 12 over 2 plus x plus 2. I don't want that there. I want a negative, so I'm going to make everything negative. Now when I say everything negative, I'm not talking about the inside of the parentheses. I multiplied those 3 terms by a -1. The other thing I need is for this number right here to be +1. So if I divide everything by -2, I get 6 over 1 minus x plus 2 over -2. As a series, it's going to go from 0 to infinity. My a is 6, and my ratio is x plus 2 over -2. Okay? It doesn't say anything about finding endpoint representation. It doesn't say anything about finding interval of convergence. However, I want to do that anyway. I want it to be practice. And maybe that was a mistake on my part not including that in the directions. But let's go further. I want this x plus 2 over -2's absolute value to be bound by +1. When I take the absolute value of -2, I get +2, and if I multiply it on both sides, what I'm really doing is bounding x plus 2 by 2. Okay, so again, I took the absolute value of -2, making it +2, and then multiplied both sides by it. This turns into -2 less than x plus 2 less than 2. Subtract 2 on both sides, and you end up with an interval of convergence of -4 to 0. A good check to make sure you did it correctly is that your center point, -2, should be exactly in the middle of your 2 endpoints, and it is. Again, I'm not checking -4 and 0 for endpoint convergence because in a geometric series, those numbers are going to give you a 1 in your ratio part of the geometric series, and 1 is going to be divergent. Okay, we've got another one. I'm going to start by putting it in the right order. I think I'm going to center it at this point. Remember that I'm centering just the x. So look at what I just did here. By centering the x, I added 3. And really, what am I adding? But a 3 and a 2 in front of it. So I just added 6. I have to balance with a -6. Divide everything by negative 11. Because I divided by negative 11, that actually gave me the negative that I needed here, okay? I could have divided everything by, or multiplied everything by a negative first and then dealt with the 11, but I didn't. Either way, I have to have a negative here, and by dividing by a negative 11, it gave me the negative I needed here. Okay, so my series has an a value of negative 1 over 11, and it has an r value of 2 times x plus 3 over 11 to the nth power. If I squeeze that 2x plus 3 over 11's absolute value to be less than 1, and I bring the 2 out and I bring the 11 out, then I multiply by 11 over 2 on both sides, leaving me x plus 3's absolute value less than 11 over 2. That means that I'm squeezing x plus 3 in between negative 11 over 2 and positive 11 over 2. Whoops, I forgot my plus 3. Subtract 3 on both sides. Well, 3 is really 6 halves, so it's 11 over 2 minus 6 halves. A negative 11 over 2 minus 6 halves, and positive 11 over 2 minus 6 halves. So this is going to be negative 17 halves and positive 5 halves. And negative 3 should fall exactly between those two numbers. Just to be sure, this is 2.5 and this is negative 8.5. Negative 3 is 5.5 away from both of those. Okay? And that is the end of that portion. Now operations. Operations with these power series representations. It says properties of functions defined by power series. If the function given by f of x is equal to that formula and has a radius of convergence that's greater than 0, then on the interval c minus the radius and c plus the radius, or the interval of convergence is what they're talking about, f is differentiable, therefore continuous. Moreover, the derivative and the integral, or antiderivative, are as follows. So if this is the formula that we're looking at, power series that we generated that's centered about the c value that's written, then we can take the derivative, and just like a normal power series, we can bring the n down and replace it with n minus 1. And just like a regular integral, we add 1 to the exponent, divide by that, and add c. Those are two possible ways to jump to a power series representation from something we wouldn't be able to do very easily. Okay? Let's do a little practice and then I'll explain more of what I'm talking about. Determine the intervals of convergence for the original, its derivative, and its antiderivative. Okay, so we did this question previously. I find it a few pages back. Excuse me. Negative 1 to 1. So the original series had an interval of convergence of negative 1 less than or equal to 1. This was exercise number 7 in 9.8. Okay. And it says find its derivatives and its antiderivatives interval of convergence. So again, before I tested the interval of convergence, it was just -1 to 1. So keep that in mind. That interval of convergence is going to be there regardless. So the derivative would be as if I brought down n and raised it to the n minus 1. And we're going to look at this interval, or this series, as itself, its own representation. Okay? This series, x to the n minus 1, what would happen if we plugged in -1 into it and +1 into it? So those endpoints aren't going to change. We're just going to evaluate those at the end, or at the value here. So what does the series -1 to the n minus 1 give us? And what does this series +1 to the n minus 1 give us? Well, +1 is just going to be infinity. You're adding 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 infinitely many times. So this side's divergent. And over here, if I'm taking -1 and raising it to the 0 power, and then I'm adding -1, +1, -1, +1. So this is divergent, but for a different reason. This is an alternating series, and the limit is not 0. The limit is either -1 or +1. It's not going to give us a finite number, one finite number. So my interval of convergence for the derivative is -1 to 1 with no endpoint convergence. My antiderivative in this case 1 to infinity is going to give me x to the n plus 1 over n times n plus 1. Okay. I'm going to simplify this to x to the n plus 1 over n squared plus n. What would happen if I looked at this series and plugged in -1? Or if I looked at the series and plugged in +1? Okay. The first one is an alternating series, and an alternating series has two criteria. The first one, what is the limit of the non-alternating part? Well, if I plug in infinity for my denominator, I'm going to get infinity over all. I get 1 over infinity, which is 0. Therefore, this is convergent according to the first criteria. The second criteria is plug in numbers. If you're not sure, what you can do is go to your calculator. Give me a second here. And I'm going to type in my non-alternating piece into my y equals 1 over x squared plus x. And I'm going to look at the table. What do you notice about the terms? Are they getting smaller? And they actually are, very much so. So both criteria fit, therefore this side is convergent, according to the alternating series rules of convergence. Over here, I get 1 over n squared plus n, and I'm going to compare that. I'm going to do a direct comparison test. No, I'm going to do a limit comparison test with 1 over n squared. 1 over n squared is a convergent p-series. This is a larger denominator, which means it's a smaller fraction. If that's convergent and this one's smaller, it's forced to be convergent. Therefore, I have two convergent series. The interval of convergence for the integral is -1 to 1, but both of them have convergent endpoints. Okay? So you can see that in all situations, we have three very different endpoint convergence based on our derivative, our integral, and the original. The original was only convergent on the -1 side. The derivative was not convergent in either endpoint, and the integral was convergent at both endpoints. second. I didn't see that I had room. Okay. The last thing we're going to do is look at why this would be super beneficial. The natural log of x centered at c. Determine the intervals with its derivative and its antiderivative. Okay, what would be the benefit of doing this? So, what do you recall about the derivative of the natural log of x? Hopefully you remember that the derivative is 1 over x. And this 1 over x falls kind of into the category of what we've been talking about in this chapter. We've got these formulas that look like the sum of geometric series, and this one looks similar, but it's missing the r value, or missing the 1 value for now. That doesn't mean that it will continue to miss it, it just means we have to manipulate it ourselves. So 1 over x is the same as 1 over 1 minus x. But not yet. What did we have, or not 1 minus 1 over x, sorry. We want to get there. So one thing that I can do is put in a 1. But I can't just have 1 without another one. Actually, I'm getting all over the place. First thing I want to do is center it. Goodness gracious. Okay. So now I have 1 over x minus 1. But if I center it, I have to also bring in that 1 that I subtracted. It's got to balance out. Therefore, I have 1 over 1 plus x minus 1. But I need a minus here, so I'm going to minus all the way through. Therefore, I have the formula, the series, geometric series, so I'm going to use a 0, of negative 1 times x minus 1 to the n. Oh, nope, not yet. What did I do wrong? This is supposed to be a positive 1. So I'm going to divide everything by negative 1, but I have to keep that minus here, so I'm going to have to put a negative 1 in the formula. Sorry about that. Okay, so we've got 0, 1, x minus 1 over negative 1 to the n. Okay. And I'm going to look at its interval of convergence, and I'm going to look at its derivative and its antiderivative. So right here, if this is a geometric series, I'm going to bound it less than 1. The absolute value of negative 1 is 1, so I'm going to ignore that, and I'm going to squeeze x minus 1 between negative 1 and 1. Add 1 to both sides, and I get x, and I get 2. My 0 plugged into this original function. I'm going to actually utilize the room that I have up at the top here. If I plug in 0, where I had x, I end up with negative 1 over negative 1, which is 1 to the n. And clearly that's going to be divergent because I'm adding 1 over and over. So I'm going to solidify this less than symbol. I'm going to make it nice and thick so that I remember that I already went through the process. I'm going to go back and look at what would happen if I had a positive 2 in there. Two minus 1 is 1 over negative 1 is negative 1, and I have the interval, or I have the, sum series, negative 1. Negative 1 to the nth power, from going from 0 to infinity, is 1 minus 1 plus 1 minus 1 plus 1 minus 1. And it's not getting you to one solid value. It's alternating between values. Its limit is not 0. Okay? So this one is going to also be less than. There's my interval of convergence for the original. Now we're going to evaluate the derivative and the integral of 1 over x, which is in turn going to help us Actually, I said of the original. This is of the derivative. Derivatives, interval of convergence. We're going to be able to figure out natural log's interval of convergence by doing the antiderivative of it. So if I take the integral of 1 over x dx, in other words, if I take that formula that we just came up with as our answer, so this is a little bit confusing. Even though this is the derivative, I'm going to treat this as the original. So that when I take its antiderivative, I'm going back to the other. I'm all over the place. Okay, so natural log 1, brain fart, here we go, x minus 1 over negative 1 to the n. The integral of it would add 1 over n plus 1. Okay, what would this become if I started plugging in 2 and 0 into my two sides? So let's see, if I plug in 0, what do I get? 0 minus 1 over negative 1 is going to be positive 1 to the n plus 1 is still 1 for n plus 1. And if I plug in 2, I get 1 over negative 1, which is negative 1, to the n plus 1 over n plus 1. Okay, I'm going to talk through this one. I'm not going to show all of the work, so I apologize for that. 1 over n plus 1 looks a lot like 1 over n. 1 over n is a divergent p-series. It's the harmonic series where p is equal to 1. If I do a limit comparison test with this, I get a value of 1. Therefore, they're both divergent. Okay? This is an alternating series. It needs two criteria to be convergent. The first one is it equal to 0 when you take the limit? And the answer is yes when I eliminate this piece of it. The second one is if I plug in a number, do I get a smaller, is it a decreasing series, better yet? So if I plug in 1, plug in 2, plug in 3, am I getting a smaller answer based on the fact that I'm getting a larger fraction, and the answer, or a larger denominator, and the answer is yes. So that is convergent. Therefore, the interval of convergence for this integral would be, what were the numbers? 0 and 2, 0 and 2. So let me pause in my thoughts. For the function natural log of x, my interval of convergence, because the natural log of x is the integral of this, is 0 to 2. The derivative, even though I treated it like the original, because then I took the integral of it, I can't take the integral of the natural log of x. So the derivative of 1 over x gave me an interval of convergence. That was what I treated as my original, 0 to 2. And I will not be able to do the integral because there is no integral of this, and the integral of this is that. So this is what I'm limited to. I could take a derivative of this, but that's really not going to help me here. So I'm going to go back when I revise my notes, and I'm going to fix the wording of this. But that's what I'm looking for this function to be figured out. Now, I went through and did some more work on my in my notebook, I think, but I'm not worried about it. No, I guess that's exactly what I did. Okay, so those are my answers, and I was able to figure out my original formula, my original interval of convergence based on my derivative by taking the antiderivative.